Can everyone hear me? Yeah, all right. Okay, let's rock and roll. So round two of the Celestial Holography Extravaganza. As ever, some recommended bedtime reading if you're interested in this stuff. But let's just remind ourselves what we learned last time. So last time we said that there was this other basis of solutions to massless wave equations called the conformal primary basis. And that this is like sort of equal to, in quotes, the Mellon transform of usual momentum eigenstates. And the reason why we cared about this was because this conformal primary basis makes the S matrix, or scattering amplitudes, look like 2D conformal correlators. On the celestial sphere. Where here the celestial sphere is in the game because we can parameterize any null momentum in 4 dimensions by a point on the celestial sphere and a scale, and the scale is the thing that we integrate out in this Mellon transform and trade it for a conformal dimension. Okay, and these things sort of look like incoming, outgoing of x. They depend on some point on the celestial sphere, z bar, and they look something like, let's see if I can remember now, something like plus or minus I delta gamma of delta over z x z bar to the delta. Okay. Now, I gave you this big sermon yesterday about what values of delta swept out a complete normalizable set of solutions to the wave equation. But of course, it's also the case that that this thing solves the wave equation for generic complex delta, the same way that momentum eigenstate, a plane wave e to the I p dot x, solves the massless wave equation for any null p, whether it's real, complex, doesn't really matter. Okay, but some of you who've played this game before or were particularly astute yesterday may have noticed that these things aren't really well defined for all delta in C. So why not? Because of this gamma function that's hanging out in the numerator, right? So the gamma function is not a smooth function on C. It has poles at all the integers sitting on the negative real axis. Okay. So why? Because this gamma of delta blows up for delta equal minus n for all n in the natural numbers union 0. Okay? So you might just say, okay, there's some bad values of delta where this Mellon transform that we use to define the wave functions just doesn't work, gives some sort of singularity, and we should just steer clear of these negative integer values. This is a set of measures 0 in the space of all the deltas, and we just live our lives happily. But it turns out that these things, these poles that happen when delta takes these negative integer values have a very physical interpretation, and the first thing I'd like to talk about today is just this, this fact. So let's let O of omega z, z bar, be any momentum space quantity. So I'm being deliberately vague about this. If you want something concrete, imagine that this is some momentum space scattering amplitude where I've, say, done the Mellon transform in all but one of the external particles. There's only one left. in momentum space, and that's got frequency omega and position z bar on the celestial sphere. So if we assume that this quantity admits a Laurent expansion in frequency of the form some sum, say from k equals minus, I'll call it n max up to infinity, omega to the k, curly O, k, z bar. So we're going to assume that this quantity, again, whatever it is, admits some power series expansion starting at some finite order in 1 over omega and then going the whole way up to all positive powers of omega. And we just call the coefficients in that expansion curly O sub k. So this, I mean, this, you might think that this is a pretty strong statement, but in fact, we're only going to need it to hold for all frequencies or energy scales less than some scale. So as long as there's some scale below which this quantity admits this expansion, we're going to be able to say the things that we say. And this is true. So an expansion like this typically exists, for instance, for perturbative scattering amplitudes in a reasonable quantum field case. Okay. So we'll maybe add one more assumption, which also seems pretty strong, but in the large frequency limit, this thing is kind of exponentially damped. Of course, that's not always true for all scattering amplitudes. Just think of GR, tree level. This admits perfectly well-defined scattering amplitudes, but they definitely don't. They're definitely not soft in the UV. So not all scattering amplitudes would obey that you would meet on the street, so to speak, would obey this this property. But let's for now just assume that this is the case. So now let's let O delta of z bar be the Mellin transform of O of omega z bar. So we just Mellin transform, do the integral from 0 to infinity, d omega, omega to the delta minus 1 of this guy, our favorite quantity that has these sort of generic features. And then we can consider for all k in the set of integers running from n max all the way down through all the negative integers, we could consider the following limit. The limit where delta approaches k of delta plus k times our Mellin transformed object. So what does this actually mean? I mean, this is just lim delta goes to k, integral 0 to infinity, d omega, some sum L from minus n max to infinity, omega to the delta plus L minus 1, curly O L z bar times delta plus k. So all I've done here is plug in this Laurent expansion into the definition of the Mellin transform. Just carrying the limit along with me for now. And this actually, because of this assumption of exponential damping and the assumption that this Laurent series holds below some energy scale, we can just forget about, for the purpose of taking this limit, forget about the high energy regime of the integral. It's not going to do anything interesting because it's just going to be tamed by that decaying exponential. So we only really need to consider the integral up to this kind of scale omega star. Don't really care what it is, just care that it exists. So then what we're left with is this limit, omega star, 0, d omega, delta plus k, sum L's minus n max up to infinity, omega to the delta plus L minus 1 with these coefficients OL. Okay. And again, this is just algebra, not doing anything interesting here, but we can break that sum apart into kind of 3 distinct regions, if you like. There's first the sum that's kind of below k. Then there's the sum above k. And then there's the term that where L is exactly equal to k. Okay. So again, not done anything fancy here so far. I've just taken the Mellin transform of this object, considered the limit where delta goes to some, well, in generically negative integer value, and then weighted with delta plus that, and then just used the definition of the Mellin transform and just rearranged the sum. Now, it's an exercise for the reader, not a hard one, to show that all of these terms and all of these terms are 0. They integrate to 0 in this limit. Okay? The only term that might not integrate to 0 is this one. And you can see why, because there's some prefactor going to 0 here, but then there's this exponent, this bit of the exponent is going to go to 0, and I get a 1 over omega. But I'm picking out the small omega regime, so that could potentially fight against the 0 that I'm getting here and give something that's not vanishing. Whereas everywhere else here, you're getting killed by the 0 prefactor, and the exponent of omega is not doing anything that can fight against it, basically.
Sorry, what happens when k minus 1 is less than minus max?
When k minus 1 is less than n max, then I guess, sorry, if I need to rearrange the integers in my head here, then we don't have a pole, right? So there's some, we assume that the Laurent series has a finite extent in 1 over omega.
Okay, so then like the sum, you have the expansion down there.
Yeah, there would be no terms. Yeah, sorry, Jeffrey. Yeah, there would be no terms in this first set of this first set of things. Okay, so there's only one interesting term in this limit. Now, why is this so? Ah, crap. Sorry, delta's going to k. These should all be delta minus k, of course. Sorry, guys. Where else have I screwed that up? Right, okay. Oh, geez, I've screwed up the exponent everywhere as well, haven't I? Just here. Okay, right, so we're looking at a limit like this, but this is actually equal to a Dirac delta function times a number. So if you just go on the Wikipedia page for Dirac delta function, scroll down a bit, there's all these different representations of the Dirac function, kind of limits of rational functions or exponential functions you can take to get the delta function. This is one of them. So in precisely this limit, this one interesting term is going to be proportional to a delta function in omega, right? So thus, this limit that we were taking localizes on the delta equal k, on precisely this term. And the coefficient here is just a delta function in omega, so we just do the integral against that. And we just get 2 times the coefficient of k in our Laurent expansion. Okay? So the upshot is that poles, when delta takes these negative integer values in a conformal primary wave function, or any object that we've built out of these conformal primary wave functions, these are coming from terms in a kind of 1 over omega expansion of the object that we started with, right? So that's like a small omega expansion. So these are because they're associated with poles in a kind of 1 over omega expansion, people called these sort of conformally soft poles. Okay, so by soft here I mean, in the usual physical sense, we think of something being soft in momentum space, something where we take the energy of our wave function to 0. That's like sending omega to 0. And the claim here is that the poles in this gamma function that kind of just appeared when we did the Mellin transform are precisely picking out terms in a kind of 1 over omega, a soft expansion of whatever object you built out of the wave functions. Okay? So these things are called conformally soft poles, and it motivates a definition of what you might call conformally soft wave functions. Yep. I'm really, the something charge?
BMS charge?
The BMS charges. Yes, but not in a way that I'm going to explain to you now.
Okay.
So yes, you're absolutely right. So it turns out that maybe the first kind of few terms in this discrete series can be mapped onto BMS.
Okay, for the
Yep. So far, okay, so these things, in some sense, live naturally on the celestial sphere because the coefficients in this expansion just know about z and z bar. So in some, okay, now I'm really waving my hands, and you shouldn't kind of take anything that I say here to the bank. But there's some rough sense. So okay, let me finish the sentence I'm writing here, and then let me try to address your question. So if I had, say, you could define some conformally soft wave function, let me call it HK, maybe I'll put the K upstairs for fun, to just be the residue at delta equals K of our conformal primary wave functions that we wrote down before. If this thing was a conformal primary graviton, and K was like 0, then the H0 here would be a generator of super translations on Scry. I'm not going to prove this for you here, but this is the connection. But you see there's way more than BMS in here, right? That's just one of these poles. You might go a little bit higher. You might find something called super rotations, if that word means anything to anyone in the... You haven't heard anything that should, in this school so far, that should make it mean something to you, that perhaps in your... Yeah, so then we lose the kind of asymptotic symmetry interpretation of these things. And something I'll talk about tomorrow is what the interpretation of those higher poles actually is. Yeah, please. Mm-hmm. There is a way to think about this. Hopefully we'll say something that makes it a bit clearer. I mean, okay, let's go off-piste in the interest of trying to answer some of these questions. So these things are all appearing in some solution of the free massless wave equation, let's say. Those solutions can be given by characteristic, say, initial or final data on Scry. So in some sense, these coefficients are like coefficients in an expansion of some sort of expansion of that data. That's the sense in which there's some kind of boundary analysis happening here. But that data is already on Scry. It's not like we're taking some like 1/r expansion. Very roughly, you could think of it as some sort of spherical harmonic expansion that's going on. That's a lie, but that would provide some intuition here. But I've not shown you anything precise that should make you believe what I've just said. Yeah, absolutely. They're wrong.
First sum?
Yeah.
L from minus M max to minus K max?
Yeah, that looks right. So obviously, when I was writing the notes, I decided to change conventions here. Does that look a little healthier? So here's my minus K term, minus K plus 1. Yeah, okay, yeah, does that sound vaguely plausible? Yeah, apologies for the notation. No worries, good catch, yeah. Okay, so for now, let's put a pin in this discussion of these conformally soft wave functions. We'll meet them again soon. But for now, like I say, I hope I've sort of justified this terminology of conformally soft poles associated with the simple poles coming from this gamma function. They have some kind of vague origin. They're not just some fake thing that appeared as a consequence of the Mellin transform. But okay, let's sort of zoom back out for a moment now. So I said yesterday that the kind of pipe dream of celestial holography was that you could use the fact that these conformal primary wave functions transform like conformal primaries on the celestial sphere to hope that there was some kind of dynamical CFT that lived on the celestial sphere that would actually compute things like scattering amplitudes for you as its correlation function. But that pipe dream, you can run it the other way around, and it's less ambitious, which is just to say you should be able to leverage the presence of this conformal symmetry to learn something new about scattering amplitudes. Okay? And that's the thing I'm going to try to talk a little bit about now. So to do this, we need to talk about something called collinear limits. Okay, now this is, if you're a scattering amplitudes person, this is something you do in your sleep. But let's suppose we're not all scattering amplitudes person. So we're recall we can parameterize null momenta in 4D with our favorite spinor helicity variables and a scale, omega. So Z and Z bar are homogeneous coordinates on the Riemann sphere, CP1. And if this is a Lorentzian real momentum, then this is the holomorphic and the anti-holomorphic coordinate. If it's a complexified momentum, then these are homogeneous coordinates on two separate copies of the Riemann sphere. Okay. So we can always go to some patch on the Riemann sphere that looks like C, so some affine patch, where, say, Z alpha is equal to some complex number little z, and Z bar alpha dot is equal to. The minus ones here are a convention that's going to make our life easier later on. It could be 1, it doesn't matter. Okay, so these are the complex stereographic coordinates on the sphere that one typically encounters when reading papers in this subject. But I want to, if you walk away from these lectures with nothing, walk away with the memory that when you work with these things, you've explicitly broken Lorentz invariance. Right? These are not global coordinates. This complex number, these are not global coordinates on the sphere. This is why I always try to write things with these alpha dot indices. Only if you can write the expression in terms of homogeneous coordinates is the thing actually Lorentz invariant. Right? Okay, anyway, sermon over for now. Okay, so any scattering amplitude of massless particles in momentum space will be a function of the kinematic invariance or Mandelstam invariance pi dot pj. Right? These are the only kind of Lorentz invariant quantities I can build out of these momenta. Now, of course, if the particles have spin, I might have some polarization vectors in the game. But we saw with the gravitons that in 4D, these polarizations can basically be broken down into plus and minus helicity. And those polarizations are determined by the momenta of the particles anyway, and some gauge fixing condition. The amplitude's supposed to be gauge invariant, so it can't depend on this gauge fixing condition. So really, the amplitude has to be a function of these things. Okay?
Sorry, one thing that's already top left is supposed to be O minus A, right?
No, so this is the thing I screwed up. This should be O minus K.
Yeah, so top left should also be O minus A.
Yes. No, it shouldn't. What have I screwed up now? I'm setting minus, yeah, okay, fine, yeah. What I've screwed up is at some point I said k was a negative integer, or I said k was a positive integer and stuck a minus sign somewhere, and I've not been consistent about this. I suggest that me unpicking this is not a good use of our time right now, but I screwed it up, yeah. And now let me, as quickly as possible, erase as many of these offending formulae as I can. Okay. Okay, so a collinear limit of a scattering amplitude is when, well, exactly what it sounds. Two of the external momenta become collinear, right? And that is when, for massless momenta, one of these Mandelstam invariants goes to 0, right? So if pi and pj are becoming collinear, it means that their dot product, or their product is now proportional to, say, pi squared. The pi was null. So anytime you have a Mandelstam, one of these kinematic invariants going to 0, in principle, something could happen to your scattering amplitude. Right? It might blow up, it might go to 0, or it might be regular. Nothing interesting might happen. But it turns out that these limits produce some kind of universal behavior in scattering amplitudes, which is well known, has been known since sort of the 80s. So first, let's remind ourselves what these Mandelstam invariants look like in our favorite parameterization of null momenta in 4D. These are just wi, wj, angle bracket zi, angle bracket zj, square bracket z bar I, square bracket z bar j. Remember these angle square brackets, these are the unique SL2 invariant inner products on our two component SL2 spinners. And if I was working in this patch, an affine patch, this would just be omega I, omega j, zi minus zj, z bar I minus z bar j. Right? So you should really think of these angle and square brackets as giving you some kind of distances on the celestial sphere, and often it'll be useful to use some shorthand for writing these things. Okay. So, yeah, no, sorry, I've just written that wrong. Omega I. Thanks. Yeah, that's not a difference of omegas. Thank you. Yeah, so here, this is a good example where we've written something that looks like it's proportional to mod z minus zi minus zj squared on the plane, but in fact, because I can rewrite it in terms of these homogeneous coordinates, this really is an expression on the celestial sphere. So in the collinear limit, we can take pi plus pj, the sum of the two momenta that are going to become collinear, and we can write them as some big P. This is the collinear momentum they're approaching, plus some parameter, epsilon squared n, whoops, where this big P, this is the collinear momentum, and this n is some fixed null vector. So this is just a simple linear algebraic statement that you can always write the sum of two null momenta as an arbitrary parameter times a fixed null momentum plus some other null momentum. Okay? You can this statement is true generically. It doesn't have anything to do with the collinear limit, but in the epsilon goes to 0 limit, it's saying that pi and pj become collinear with p. Okay? And we assume that big P is null. So generally, the universal behavior in the epsilon goes to 0 limit of a scattering amplitude, which is where pi plus pj goes to p, some scattering amplitude in momentum space, which is a function of a bunch of momenta, two of which are pi and pj. This is given by some sum, call it over h, of some kind of universal splitting function, this is called the collinear splitting function, times a scattering amplitude with one fewer particle, where instead of pi and pj, we've lost these two, and instead we just have one collinear momentum left over p. Okay? This sum is over the quantum numbers that this new particle can carry. Right? And what those are depends on what the two collinear particles were to begin with. Okay? So this is sort of theory dependent, what this splitting function is. And we say that, that a theory has collinear singularities if this splitting function of ij goes to p, if this goes like 1 over epsilon, where epsilon was the parameter controlling the collinear limit. Okay? So typically one can compute these things in perturbation theory, and in some cases they're actually protected against quantum corrections to say the tree level splitting function is a universal answer for the whole theory to all loops. Not always the case. Okay, so for instance, let's consider an example. Consider two positive helicity gravitons with momenta pi and pj becoming collinear. Okay. Then it's been shown that the only splitting function you get, so I'll put this superscript plus to remind us that they were positive helicity, is when these guys go to another, their collinear limit produces another positive helicity graviton, so I have plus plus into plus. You might say, well, what about if I wanted to produce a negative helicity graviton? Coupling just isn't there in GR, for instance. This thing is, all right, I'll be careful about all the signs and factors now, and then I won't be later. So here cap this is the gravitational coupling constant. So this is just a computation that one can do. It turns out that this is one of the examples of these protected collinear splitting functions. The tree level answer is exact. Okay. So, okay, cool, this is some nice result. But actually, it's easy to see there's a statement one often hears if you hang around in this kind of amplitudes crowd long enough. You hear things like, gravity doesn't have any collinear singularities. Right? But we just wrote this splitting function. But it's easy to see why this isn't singular. Right? So in the collinear limit, we have pi dot pj going to 0. Right? But that's the same as saying that mod zij squared goes to 0. So for Lorentzian real momenta, zij is going to 0 as fast as z bar ij is going to 0. So this isn't actually singular. So this isn't actually a collinear not actually a collinear singularity in GR. It's something completely regular for Lorentzian real momenta. But what is our favorite thing to do when we wake up in the morning? To consider complexified momenta, right? And in that case, you can produce a singularity here. So if pi were allowed to be complex, we could consider a limit where zij went to 0, but z bar ij was held finite. And this is something called the holomorphic collinear limit. So GR doesn't have interesting collinear singularities for Lorentzian real momenta, but it has interesting holomorphic collinear singularities. It's clear why we call this a holomorphic limit, because we're allowing the zij's to get close, but we keep the z bars fixed. So we don't do anything with the kind of anti-holomorphic degrees of freedom on the celestial sphere. You can't do this for Lorentzian real momenta, but you can certainly do it for complex momenta. Good. So I haven't told you anything yet that should justify why you should want this. In a moment, I hope to answer this this question. Yeah.
Should I worry that this positive helicity graviton splitting function sort of depends on the phase that I approach 0 in the complex plane?
You could worry. It turns out that it doesn't. Yeah, good. So there's, I mean, you could think of this phase as like the kind of longitudinal momentum split. So you could worry that it depends on this. It turns out that it doesn't. But there's no, I guess, a priori reason why it shouldn't. Other than, well, actually, sorry, I say that. I guess there's probably some Lorentz invariance argument that prevents it from doing this. If it did in the strict collinear regime, I think the answer wouldn't be Lorentz invariant. But let's not, should have turned the microphone off when I said that. Yeah. That is exactly what we're trying to do. Yeah, that's exactly what we're trying to do. So good, so this, so gravity does have holomorphic collinear singularities, which are controlled by these zij limits going to 0 on the celestial sphere. And this should absolutely ring some kind of 2D CFT bell for us. And that's the whole point. So consider some 2D CFT with some primary operators. Let's call them curly O I, Z I, Z bar I, curly O J of dimension delta J at Z bar, at Zj, Z bar J. So take your favorite 2D CFT, take two local conformal primary operators in that CFT. Then conformal invariance dictates if you like the short distance behavior between these operators. In terms of something called the operator product expansion, or OPE. Okay, so what does this look like? It says that if I have O delta I, Zi, Z bar I, O delta J, Zj, Z bar J in my CFT, that I can write their product in terms of a sum over all the admissible scaling dimensions in the theory times some coefficients, Ci, J, delta, which are functions of the separations between the two operators, holomorphic and anti-holomorphic. And these things, they don't have to be functions. They can be differential operators in general, which have holomorphic and anti-holomorphic derivatives in them, acting on all the other primaries in the theory evaluated at Zj. These things, called the OPE coefficients. And they are generically singular in these separations, Zij, Z bar ij. Okay. So if gravitons could be represented by some local operator insertions on the celestial sphere, then their short distance behavior would be governed by an operator product expansion. But we already know that this operator product expansion is precisely controlled by the short distance behavior on the celestial sphere corresponds to these collinear limits that we were talking about. So the idea is that collinear limits in momentum space should correspond to operator product limits on the celestial sphere. Because they're both governed by Zij, Z bar ij going to 0. Okay? And just like how in 2D CFT, we typically have chiral splitting and we can disentangle holomorphic and anti-holomorphic degrees of freedom, we've seen that we can do the same thing for collinear limits by considering holomorphic collinear limits, or if you like, anti-holomorphic collinear limits. Okay? So this is like sort of a two-way street. You can study collinear limits and then take their Mellin transforms and, yes?
You said that gravitons doesn't have collinear singularity, but then doesn't it imply that there are no OPE for gravitons?
No, it implies that the OPE could be chiral in nature, like this one. Right? So in a 2D CFT, you could have, in principle, OPE limits that look like this. So if you really set Z bar ij to be the complex conjugate of Zij, this wouldn't produce an OPE singularity. But in the language of 2D CFT, we would absolutely consider this to be a singular OPE coefficient. Good question. Okay. So yeah, this is a two-way street, as ever with this celestial holography stuff. You can study the collinear limits one knows and loves in momentum space, try to run them through this Mellin transform, and learn something about the OPE limits of a celestial CFT if it exists, right? Or you could go the other way around and say, well, I know a lot about OPEs of 2D CFTs. Can this teach me anything I don't know already about collinear limits? Okay, so always with this celestial holography stuff, there's some two-way street. Usually one of the ways is super ambitious, and the other way is somehow more practical. Okay? But for this particular thing, I think it's fair to say that we've learned things in both directions, and that's what I'll try to convince you of in the last half hour here. Okay? So we're going to concentrate on the example of two positive helicity gravitons and the holomorphic collinear limit that we've just defined. Okay? Yep. So if I have two particles of the same helicity in a parity invariant theory, they can't fuse and create a particle of different helicity. But I can take a collinear limit of a positive helicity graviton and a negative helicity graviton, and then I could produce gravitons of both helicities. So I've made our lives simpler by considering this same helicity configuration. Yeah.
You said that the movements can be reversed. And my question is, this universality is like more than
Yeah. You could view it a little bit in this way. So yes, so the same way that in some sense singular bits of an OPE limit are kind of dictated by conformal Ward identities. This is true. What you can't learn from the CFT structure is that this thing is exact to all loops in perturbation theory. So what CFT tells you is that it kind of has to come with a pole of some order, right? But you could have some non-trivial function of kappa upstairs, for instance. And so the following is not a proof that this thing should be. So for instance, in gauge theory, if I was taking two positive helicity gluons going to a positive helicity gluon, that thing gets loop corrections in 4D. And somehow, the reason for this is very, very roughly speaking, if you were getting loop corrections, these things would come with powers of the coupling. The coupling's dimensionless for gauge theory in 4D, so you can build interesting functions. Here, the gravitational coupling constant is dimension full. So suppose I had some kappa squared correction to this. It has to have the same dimensions as the tree level result. So it has to come with some Mandelstam invariants, but the only Mandelstam invariants I have in the game are going to 0. This isn't a proof, but it's some intuitive explanation for why the thing doesn't get loop corrections in gravity. But the CFT side of the argument doesn't tell you anything about the kind of function of kappa. In principle. I mean, that's the pipe dream here. I think it's fair to say that that's not been realized, because I should emphasize here, for those who aren't kind of CFT practitioners, often we say, well, the CFT is like, why we love CFTs is they're kind of axiomatic in nature. If you know all of these OPE coefficients, and you know this set I of admissible operators and their dimensions, then actually you know every correlation function in the CFT. But there's some implicit assumptions that go into that statement, like unitarity and locality. Those don't go into the structure of the OPE. Any CFT will have an OPE of this form. But the idea that you can uniquely determine correlation functions just from the OPE data, there's some link with locality and unitarity there. And it turns out that we'll see this later, tomorrow, one can very easily show that if a celestial CFT exists, it's not local, for instance. So if you're a conformal bootstrap person, this is when you kind of flip the table and walk out of the room, because what's the point of a CFT if I can't bootstrap it? Or so I'm told repeatedly by my friends who are CFT people. But yeah, it's a good point. Okay, so all right, let's embark on this adventure. So. What statement? No. So the statement I'm making is that the bootstrap program requires unitarity and locality. OPE is a generic feature of any CFT. It's just a statement about conformal invariance. You need crossing locality and unitarity for the bootstrap program to work. And I haven't told you anything so far that should make you believe that if there's a CFT that's computing amplitudes in the conformal primary basis, it should be local or unitary. Okay, so let's consider one of our celestial amplitudes, which we called m twiddle, and we're going to assume that this thing, in addition to being a function of a bunch of other particles, in particular, it's a scattering amplitude that involves our two positive helicity gravitons, and this is given by, remember, a bunch of Mellin integrals, k equals 1 to n, d omega k, delta k minus 1 times the momentum space amplitude. Right, so there's n particles in the game here. I'm assuming they're all massless. I'm just only going to be picking out the functional dependence on I and j, because those are the ones we're going to take to be collinear. I hope it's kind of clear what the expression means. So then if we want to take a holomorphic collinear limit, that means taking the limit as Zij goes to 0 of this celestial amplitude. And we know, It's an unfortunate fact that I'd just written the splitting function on this blackboard, which I've erased. Now, we know what the splitting function is in momentum space. So this is going to be given by the integral from 0 to n over all the frequencies in the game times our splitting function, I plus j plus to p plus, times the amplitude with one fewer particle, and now just omega p, z p, z bar p over here. Okay? So now it's clear that only two of these Mellin integrals are interesting in this collinear limit, the one for omega I and the one for omega j, the two collinear particles. And it's useful to do a change of variables, so parameterize omega I as being t times omega p and omega j 1 minus t times omega p. So this t in the unit interval is like the longitudinal momentum fraction. Right, so the point is that omega I plus omega j is always equal to omega p, but we can kind of parameterize how much of it I should think of as being in omega I and how much of it I should think of as being in omega j. And so then we can trade the integral over omega I and omega j, the Mellin integrals over omega I and omega j, in here for an integral over this momentum fraction and a Mellin integral over omega p. Okay, so it's just a change of variables. So this leaves us with lim zij going to 0 of our Mellin amplitude is equal to integral from 0 to 1 dt t to the delta I minus 2, 1 minus t to the delta j minus 2 times Mellin integral 0 infinity d omega p, delta I plus delta j minus 1 times z bar ij over z ij times the product of all the k's not equal to I or j, d omega k, delta k minus 1 times our n minus 1 point amplitude, which is a function of the collinear momentum. Okay, so this is just some straightforward change of variables in an integral. You might wonder why some kind of weird powers, like where did these minus 2's come from? But that's just from the splitting function. Remember, the splitting function went like omega p squared over omega I times over omega j. And then I have the kind of angular dependence of the splitting function where I have my holomorphic collinear singularity, this anti-holomorphic thing in the numerator that's not doing anything interesting. Okay? Okay, so let me be street legal. Plus order zij to the 0 corrections. I've not taken the limit yet. So now, recall that this P is our collinear momentum. So I can write P alpha alpha dot is equal to Pi alpha alpha dot plus Pj alpha alpha dot plus order epsilon corrections, where epsilon is the parameter controlling the holomorphic collinear limit. So I could just replace this with order Zij corrections. Okay. So using our favorite parametrization, so this is just reminding us of the definition of the holomorphic collinear limit, but now there's some kind of interesting algebra that you can do. This is just equal to omega I plus omega j, zj to the alpha, but not to the alpha, zj alpha, z bar j alpha dot plus omega I, z bar ij iota bar alpha dot over omega I plus omega j plus order Zij corrections, where I've chosen spinor dyad I've chosen a constant 2-spinor iota bar alpha dot to do this decomposition here. So this z bar ij, there isn't an index on this. I've moved the dotted index onto there. To check this statement, all you do is multiply everything inside the big parentheses by the stuff I've pulled out and check that it reproduces what I've written up here, plus corrections of order Zij. Okay. It's just some algebra. And this is omega p up Zj alpha, Z bar j alpha dot plus t, Z bar ij iota bar alpha dot. Okay. So why am I going through this algebraic exercise? Because over here, I've gotten my Mellin integral, or I've gotten my limit of the celestial amplitude, the kind of OPE, holomorphic OPE limit of the celestial amplitude, into a form where I have a bunch of integrals times an amplitude, integrals of an amplitude in momentum space that depends on omega p, the collinear frequency, and then zp, z bar p, the collinear momentum's position on the celestial sphere. If I want this to look like an OPE, right, the thing on the right-hand side of the OPE has to just be a function of the zj's and z bar j's, right? This is the way OPE works. You take the singular term and then you kind of, it's like extracting a residue every time. So you don't have, the coefficient of the OPE coefficient doesn't depend on Zij. It just depends on Zj. So what we've done here is we've rewritten the kind of spinor representation of the collinear null momentum in a way that makes this manifest, right? So in the holomorphic collinear limit, we can identify Zp alpha with Zj alpha up to corrections that we're going to neglect in that holomorphic collinear limit, and Z bar p alpha dot with Z bar j alpha dot plus t Z bar ij iota bar alpha dot. So that means that over here, in my momentum space amplitude, I can replace Zp by Zj, and I can replace Z bar p by Z bar j plus this order t correction, order Z bar ij correction, right? And then I can expand this function in a power series in Z bar ij. And then I'm in the ballpark of getting something that looks like an OPE. So now we can use, in fact, this n-1 point guy thought of as a function of the collinear momentum can actually be written as a function of Zj. And we can now Taylor expand this thing in Z bar ij. This is a street legal thing to do because we're keeping Z bar ij fixed, right? You could worry if you had Lorentzian real momenta, this is not a copacetic thing to do because this thing going to 0 might produce some sort of weird singular behavior here. But because we're doing the holomorphic collinear limit or the holomorphic OPE limit, this is a street legal thing to do. So what we get is the following. This angular bit of the collinear splitting function just cruises outside of all of these integrals. And what we're left with is a sum. M goes from 0 to infinity, 1 over m factorial, integral 0, 1 dt, t delta I plus m minus 2, 1 minus t delta j minus 2 times integral 0 to infinity d omega p delta I plus delta j minus 1, product over all the other frequencies that are not becoming associated with collinear particles, z bar ij to the m, d bar j to the m, acting on m, n minus 1, omega p, zj, z bar j, plus order zij corrections. Okay? And now we can rock and roll. We can do these integrals. Right? So just to clarify, everything about this sum in M, that's just the Taylor series in Z bar ij, right? Because every time I do this, it's going to kick out a power of t along with this Z bar ij. That's the thing that cranks up the exponent here. And then these anti-holomorphic derivatives, those are just the derivatives in the Taylor series. Okay. So what one gets here is that the lim Zij goes to 0 of the celestial amplitude is equal to Z bar ij over Z ij times an infinite sum, m equals 0 to infinity. These coefficients are Euler beta functions. Okay, and then this, so what's happened here? The t integral, this is just the integral representation of this Euler beta function, right? capital beta of x and y is gamma of x, gamma of y over gamma x plus y. Okay? This is the integral representation of that Euler beta function, so that's an easy kill. And then what we're left with are just these Mellin integrals, but this is precisely the definition of the celestial amplitude where particle P, oh no, sorry, we're up here, yeah. Particle P now has location zj, z bar j on the celestial sphere, and conformal dimension delta I plus delta j. Okay, so that's why I've written this delta I plus delta j here. And, okay, plus order Zij corrections, okay? But this here, we made no assumptions whatsoever about what the other stuff going on in this amplitude was. We just assumed that the two collinear particles were positive helicity gravitons, so this allows us to read off a celestial OPE coefficient. So this implies that if I have local operators on the celestial sphere which correspond to positive helicity gravitons of dimension delta I and delta j, that the singular part of the OPE has a simple pole in the separation, the holomorphic separation of those operators, times a kind of infinite tower of SL2 descendants. Okay? So from this, what we've done is we've read off some of the CFT data that a celestial CFT must have if it exists. Conversely, you can view this statement completely in momentum space terms. Right? It's saying that the holomorphic collinear singularity in gravity between two positive helicity gravitons has a simple holomorphic pole and an infinite series, regular series in the anti-holomorphic separation. Right? Zij, Z bar aj, these things are points on the celestial sphere. They're also parameters in the null momenta, right? So if you don't like Mellin amplitudes, you don't like celestial holography, it doesn't matter. This is still an interesting statement about holomorphic collinear limits. And so on the one hand, I was telling you guys about this two-way street that's sort of always in the back of our minds, at least in the back of my mind, with celestial holography. And one way of the street is this. We study something we know well in momentum space, the holomorphic splitting function of two positive helicity gravitons, and we learn this OPE coefficient, or set of OPE coefficients that should exist in celestial holography. But in fact, conversely, it turns out that these sorts of statements, not the one I've written here, but other generalizations of these statements, allow us to deduce new facts about collinear splitting functions that weren't known before. So for instance, there are certain nice helicity configurations of graviton scattering in 4 dimensions, and we now know how those can be reconstructed to arbitrary orders in the number of external gravitons by just repeatedly iterating or repeatedly taking inverse collinear limits, inverse holomorphic collinear limits. So it's like an all-order holomorphic collinear expansion of certain graviton amplitudes. Yes? Okay, so for gluons, if I'd done gluons, here you'd lose the Z bar. Upstairs, there'd still be this 1 over Zij. The structure would be very similar. What would change would be the arguments of the beta function and the conformal dimension of the kind of fused operator. There'd be a -1 here, if I remember correctly, for gluons. But the argument works in exactly the same way. Part of why I wanted to show you this one is that the gluon one isn't protected against quantum corrections, and this one is. So in some sense, this is some kind of universal statement. But yeah, you can do the same. Anytime you have a collinear splitting function that you know in momentum space, you can run this argument. Okay? All right, so in the last couple of minutes here, I'd like to sort of come back to this idea of conformally soft wave functions that we started with. So it's an easy observation that the OPE coefficients that we just derived here, they're not generically non-singular for all choices of conformal dimensions for the external gravitons. So why? That's because this beta function, delta I plus m minus 1, delta j minus 1, is, again, just the definition of the beta function. This thing has poles whenever the arguments of these gamma functions upstairs take 0 or negative integer values. So here, recall that m is running from 0, 1, 2, all the way up to infinity over the natural numbers. So it's clear that we'll get simple poles for some value of m whenever, say, delta I is equal to 1, 0, minus 1, minus 2, minus 3, all the way down the negative integers. So somehow this celestial OPE coefficient that we wrote down knows about this tower of conformally soft wave functions that we talked about at the beginning. That's not surprising because the OPE is just like a fusion rule of two of the conformal primary wave functions. If those know when they're conformally soft, then you better bet that the OPE will know about it. So what one can do is you can now compute the holomorphic OPE between conformally soft graviton wave functions. So remember, these are just the things we define, let's say hk of z bar. This is just the residue at delta equals k of, let's say, positive helicity graviton conformal primary wave function. So we just pick out the residue of the pole in the gamma function in this thing, and then we can compute say I, j, z bar j. This OPE, where we just take the OP that we've written down for generic delta and extract the residue of the beta function for these negative integers, say values k and l. And what one finds is that you get something like 1 over z ij times a sum m equals 0 to 1 minus k, some huge binomial coefficient. Okay. So this is just some residue computation. And because it's a holomorphic OPE limit, we can expand these conformally soft graviton waves functions in anti-holomorphic modes, right? Just like you would in 2D CFT. So you can expand HK, say, Z bar. There's a consistent mode expansion with A going from, say, K minus 2 over 2 to 2 minus K over 2 with some modes HK, A that only have holomorphic Z dependence over Z bar to the A plus K minus 2 over 2. The reason for these limits in the sum is so that this is actually always a positive power of Z bar appearing here. So. This is, again, consistent with the holomorphic collinear limit where we shouldn't be picking up any negative powers of Z bar anywhere, the holomorphic OPE limit. Okay. So then, if you define the commutator of modes, say HK, M, HL, N, say at Z, J, this is just residue. Well, there actually need to be 3 of these. Okay, so what's going on here? This first contour integral picks out the residue of the simple pole in the holomorphic OPE. Then these contour integrals pick out the modes M and N in this anti-holomorphic mode expansion. So this is just the definition of what we would mean by a commutator. It's just picking certain terms in the holomorphic OPE. Okay. So then how shall I say this? A non-trivial but not terribly illuminating computation, you can actually compute what this is. It's something god-awful. What's that? Yeah. So here you've disentangled a kind of holomorphic and so you're treating the holomorphic one as Virasoro and the anti-holomorphic one as SL2. So you're not allowing singularities in the anti-holomorphic. Yeah, very good. This is one of these things, I don't know, should everyone see this before they die? I don't know. you get this horrible looking thing. Okay, but the point is not that it's horrible or not horrible looking. The point is that these modes of positive helicity conformally soft gravitons form a closed algebra under holomorphic collinear limit, right? There's a priori nothing to explain why this should happen, right? And in fact, you can make these commutators a whole lot less ugly with some inspired relabeling of the modes. So if you let WP sub m be some combinatorial coefficient, then if I take commutators of these new modes, I get something stupidly simple. And this is for P running over 1, 3 halves, 2. So that's equivalent to saying that 2P minus 2 is a non-negative integer, and the absolute value of m is less than or equal to P minus 1. Okay? Yeah?
The base values where come from?
Ah,
That's W in algebra, no?
it almost. So these values came from requiring that this anti-holomorphic mode expansion only had positive powers in Z bar. So that's the thing that gives you this kind of wedge condition here. Yeah, exactly. So it's coming from the fact that we've taken only a holomorphic OPE limit. We haven't allowed any singularities in the anti-holomorphic coordinates. So that's where this wedge comes from. And it's true, as Kim correctly saw, that this algebra has these commutators look like the commutators of the loop algebra of a Lie algebra called little w1 plus infinity, and then there's some wedge condition, which is this one. But actually, this isn't quite true, because if this was really true for little w1 plus infinity, this quantity p would only be allowed to take on integer values. So this is actually something a little bit more. Okay, some mathematically precise sense. This is not the correct name for this algebra, but we'll talk, hopefully, in the Twister lectures about what the real origin for this, because so far this is like some miracle. Like, where did this come from? There was no a priori reason to expect that positive helicity conformally soft gravitons would form a closed algebra under holomorphic collinear limit. That's kind of cool. The existence of this algebra actually gives you an infinite number of constraints on certain scattering amplitudes in gravity. So if you've heard of something called MHV, maximal helicity violating scattering, that's uniquely, it turns the form of that scattering amplitude is uniquely fixed by consistency conditions with this algebra. And that's true not just at tree level. So you can bootstrap higher loop amplitudes in GR, or effective theories of gravity, which we didn't know before using this algebra. But anyway, I've gone 5 minutes over time, so I'll stop here, pick up later.